Hi guys, I'm back to talk more about soil formation, and so I will share my screen again and we will look at PowerPoint. We talked a lot about parent material so far, and parent material is one factor that has an enormous impact on the way that soil will develop in a particular area. But it's only one factor of many, and in particular, there's kind of a famous, what is often called state factor equation that kind of lays out what are also sometimes called these 5 soil forming factors. So this kind of conceptual idea about soil formation is something that was put forward by kind of a famous early soil scientist who worked in California as part of the early University of California university, a big land-grant university, which is now the UC system, and his name was Hans Jenny, so spelled Jenny, but pronounced Jenny. And he basically said that based on his observations about soil, it was a function, so that's kind of a mathematical kind of letter there, symbol there. And then in parentheses, he lists out these 5 factors, and then intentionally includes an ellipses at the end, this ... to say like, hey, this is in 100% of everything that could be contributing to the formation of soil. There's more things that I haven't been able to touch on, and maybe that we don't know that well about at this point when I'm writing this. But nonetheless, these 5 factors are really important in describing how soil forms. So those factors are climate. Is this a hot, dry area? Is this a wet, stormy area, or everything in between? What kind of organisms live there? So is this a desert? Is this a forest? Is this a grassland? And then what is deemed in his equation R, which stands for relief. So you may have heard of like a relief map before, but you may also be more familiar with a term like topography or even just slope. Like, is this a steep area? Is it a flat area? So that is going to affect how soil develops and accumulates on a landscape. And then P, parent material, we've talked about quite a bit so far. And then finally, time. So how much time has the soil been developing in this particular location? So he basically said, based on his observations, if we know these 5 things, then we can both kind of look into the future and imagine how soil will develop in an area. And also we can kind of look into the past and imagine, when we see soil, we can imagine what these kinds of conditions were like in the past to create the soil that we see here today. So it's just kind of like a framework to help us understand how soil forms. So we've talked a lot about parent material already, but I want to talk in a little bit more detail about these 4 other soil forming factors or state factors. Okay, so climate, hopefully you're familiar with, is basically something that describes the kind of atmospheric conditions of an area. And in particular, it's not necessarily just atmospheric conditions at a particular moment in time. That's what the weather is. But the climate is kind of like a more long-term idea of what's going on with the atmosphere. So there's many different things like windiness and humidity and precipitation and temperature that might contribute to climate. But in terms of soil development, there's 2 main factors: temp, or temperature, and then what we'll call effective precipitation, so the amount of precipitation that actually makes it down to the soil, that are going to be the 2 most dominant factors in influencing soil formation. So temperature is important because as the environment gets warmer, what that essentially means on a really microscopic level is that all the different kinds of atoms and subatomic particles and everything are actually just moving around faster, and that allows for faster rates of reactions. And so there's this kind of rule of thumb, back of the envelope type of thing that many biologists know, which is that as we increase in temperature by about 10 degrees Celsius, which is equivalent to increasing about 20 degrees Fahrenheit, so maybe from like 50 degrees Fahrenheit to 70 degrees Fahrenheit, we're going to double the rate at which different biochemical reactions are happening. So we might have plants photosynthesizing twice as fast, but we're also going to have different kind of microbes decomposing organic matter in the soil twice as fast. And so we're just having a lot faster rate at which things are happening, and therefore a lot faster rate at which soils are building in warmer environments versus colder environments, which is probably not really hard to imagine, right? If you stick something in a freezer, you're trying to slow down the rate that it's breaking down, or even in your fridge. Whereas if you leave it out on the counter or put it out on a sunny table on a hot day, you can see that material is starting to change more quickly. So effective precipitation, as I already mentioned, is not necessarily how much it rains, not how much rain comes out of the sky, but how much rain actually gets down to the soil surface. So there could be a lot of rain that just ends up getting captured by vegetation, like snow that falls on trees that evaporates back into the air, or raindrops that are caught on blades of grass that re-evaporate into the air. And so there's a much more limited amount of water that actually is not really interrupted or transported out off-site by plants, but is actually really available to be moving around in the soil. And that's what we call effective precipitation. So another term you may or may not have heard of before is evapotranspiration. And evapotranspiration is basically a combination of the amount of water that's evaporated off the surface. So if you have water that kind of pools up in a puddle on the surface and then it evaporates from there, that would of course not end up being effective precipitation. But also if you have some soil that maybe penetrates down into, or you have some water that penetrates down into the soil and then is very quickly absorbed by plant roots and then pumped back out into the atmosphere through the inside structure of plants, that water is considered to be what's called transpired, which is kind of like the same as perspired by humans, like we sweat things out. Well, plants do that too. And so the combination of the water lost back to the environment is evapotranspiration. So some of the rainwater is eaten up by that process, but some of it is left over, and that's what we call effective rainfall or effective precipitation. So here's a little diagram from your book that's showing we might have lots of rain, but we might have high evaporation and high plant use, so very limited effective rainfall, or we might have the same amount of rain coming in, but lower evaporation, maybe on a colder day, lower plant use, maybe because of different biota or different season of the year where plants are more dormant, and then we might have much more effective rainfall from the same amount of water in different environments. So the temperature and then the amount of water are really going to impact soil development. So we already said temperature is impacting soil development because the warmer it is, the faster things are breaking down, the faster soil is building. Water presence in the soil is really important because of the way that water reacts and interacts with materials in the soil. So water is known as a universal solvent. And a solvent is basically something that dissolves things into it. So water is good at dissolving salts and dissolving sugars and dissolving all these other kinds of compounds that are part of rocks and part of organic matter in the environment. And they do this in part because of these hydrogen bonds that they form. So water is considered to be what's called a polar molecule. And what that means is the water molecule, which is H2, 2 hydrogens, and O, 1 oxygen, is formed in such a way that the electrons, the negatively charged electrons that form around the outside of these different atoms, concentrate on one side of the water molecule. And so there's one side, kind of like the butt side of the water molecule, that has this not like full on negative charge, the same that an ion would have, but it has like a slight or negative charge. And so we consider that the molecule is polarized, meaning that it has these different sides to it. And so that polarization allows it to be a little bit more like sticky, like almost slightly, you can imagine like magnetic or something. So it can grab on and hold on and pull on different kinds of other chemical compounds or chemical, different kinds of ions and stuff in the environment pretty effectively. And those are called, like those particular bonds that these polar molecules make, especially with other water molecules, are called hydrogen bonds. So this kind of structure allows it to, the water molecules, which are supposed to be shown here by these little turquoise and black Mickey Mouse looking things, are really good at essentially like coming in and attacking rocks and attacking organic matter and then dismantling it and pulling it apart. And so when we have much more water in the environment, we're just going to be weathering rocks and minerals more quickly. And then we're also going to be kind of dismantling other organic compounds more easily as well. So this is a picture of NaCl, which you probably know as table salt, or it's also a mineral compound called halite. And so we can imagine from these two diagrams how the water is kind of pulling apart the compounds in this particular mineral. So the presence of water is going to be accelerating the rate of soil development. Okay, so then the next term in our equation, clorpt, sometimes people call it. So we talked about Cl, climate, and then O is for organisms, which are also sometimes referred to as biota, which is just like biological organisms. And of course, there's many different kinds of organisms or biota in the environment, and they can all contribute to soil development. So let's just talk about a couple of different broad groups of organisms, starting with plants. So plants obviously have important relationships with soil. Plants can add root matter. They can also, of course, add leaves as leaves fall off and decompose. So root matter is particularly important in grasslands. The type of really thick matted roots that grass is formed leads to these really deep A-horizon or topsoil formations in grassland environments, which contribute to very fertile soils. Because remember that A-horizon is like the topsoil environment where there's more organic matter and more interaction with living organisms. In other environments that contain more trees or shrubs, where the leaves may fall off every winter in a deciduous environment, or in a dry season in a more tropical deciduous environment, or just like from year to year as trees age, those kinds of things are going to break down to form more of that O-horizon that we talked about last week. And the acidity in a lot of these different kinds of leaves may actually slow the breakdown, but still it's definitely contributing a lot of organic matter through this process. And in general, trees that are like deciduous or broadleaf trees, like maple trees or oak trees, are going to have a little bit of a different quality than conifer trees that have needles. So pine needles tend to contribute more limited, what we could think of as nutrients, or in this case, what our textbook is referring to as cations. So we'll kind of do some more chemistry review later, but an ion is, remember, an atom that loses or gains electrons to have a charge, and a cation is one that has lost some electrons to have a positive charge. So many different elements naturally in the environment lose these electrons and form cations. So this is things like calcium, potassium, magnesium, sodium, which are all different kinds of nutrients that plants might need. So basically, pine needles are not as nutritious, as nutrient rich as other kinds of like just broadleaf trees that tend to have a little bit more nutrients and also tend to release those nutrients a little bit more quickly. So another thing that plants do is just the above ground structure of the plant actually can act as like a trap that captures silt and dust and then other like leaves and branches from other plants that might be blowing across the landscape. And it basically acts like a little filter, a little trap that captures all this material that's being blown across the surface. And in doing this, the plant structure itself builds up essentially like a little compost pile around itself that might be from some of its own leaves that it drops, but also from, like I said, other organic material from other organisms that's being blown across the landscape. And then, of course, other little critters might come and burrow underneath the plant and poop or die or whatever else. And so we have these little kind of rings of fertility created by this concentration of organic matter that ends up being trapped around these plants. And so these are called fertility islands. And these really help support plant growth in arid environments, which is kind of a neat adaptation Also, potentially problematic adaptation, because when we start to remove native vegetation from these kind of native landscapes through overgrazing or just through development, or through like draining of groundwater, things like that, then it can be really hard to revegetate these areas once those little fertility islands that are supporting plant growth in very specific areas have disappeared. So it's a lot easier to remove vegetation than it is to get it back. Anyway, so that is an influence of plants, and basically, hopefully you can imagine that in all of these cases, the presence of plants is helping to contribute organic matter and build more soil and build soil faster than if plants were not present. So the same thing is going to be true for animals. The presence of animals is helping to build and develop soil. So one of my favorite soil terms is pedoturbation, or sometimes people call it petoturbation. I've heard both. But basically it's like the mixing of the soil, right? Turbation, turbidity. And so you can imagine like this little earthworm is like diving down into the soil and then coming back up and diving down and coming back up. And through that process, it is essentially like blending up and mixing up the soil. So it's redistributing this organic matter that's falling on the surface, it's carrying it down, it's pooping down low, it's coming back up. So it's mixing in organic matter, and then it's also aerating the soil. It's bringing oxygen down by creating these little tunnels, which later we'll talk about as macropores, large size pores in the soil that can contribute to the life in organic matter and organisms living farther down deep in the soil, which is also going to be better and allow for more soil development. Humans, of course, are animals too, and we can have a pretty outsized impact on soil. So we do a lot of things that can damage soil, but we can also help soil and build soil in areas where we focus our energy in positive ways. So a couple of things that might impact soil development that humans do are things like removing native vegetation, as I just mentioned. So we know that the presence of that vegetation is helping to build soil. We can irrigate in areas that are dry. And so in some ways that might help build soil because there's more water, but as we'll talk more about later, that might lead to like salt accumulation and changes in salinity of the soil, which might be harmful. We can add fertilizers, which may, again, in short term, boost productivity, but in long term, change soil chemistry and impact soil biodiversity and whatnot that can have long-term negative impacts. And then of course we like to move soil around. So we like to bring in topsoil and we like to scrape soil, clean and make road beds and make building beds. So we do a lot of things that can influence the way that soil is developing. Okay, finally, microbes. So microbe is a word basically like for things that aren't plants or animals. So that could be like fungi, bacteria, protozoa, etc. And many of these organisms have an important role in decomposition. So as they're decomposing other organic matter in the environment, that's helping to build and develop soil. So more microbes is going to yield more soil, faster soil development. So in grasslands, this kind of decomposition role tends to be dominated by bacteria, with some fungi present as well. And in forests, we tend to have a lot more fungi and not as many bacteria in soil. So down here is a picture of chanterelle mushrooms, which you may have eaten before or heard of people eating before. And these are important forest land fungi that have relationships with different kinds of trees. So these chanterelle mushrooms, like many other different kinds of fungi, as well as bacteria, have different kinds of symbiotic relationships with many plant organisms in the soil environment, where they help supply the plants with different kinds of water and nutrients, and then the plants feed them different kinds of sugars. So that's what a mycorrhizae or a mycorrhizal relationship is, and we'll talk more about that later. Also, many bacteria are good at what's called fixing nitrogen, which is basically transforming nitrogen from an inorganic form of nitrogen to what's called a bioavailable form of nitrogen, and that's something that most organisms can't do. But bacteria can take nitrogen out of the air and then turn it into fertilizer, which the only other organism that can do that is humans, and we do that at the cost of an enormous energy input and pollution production. So it's pretty neat that bacteria can do that all on their own. So if we're in a healthy soil ecosystem that has these natural presence of nitrogen fixing bacteria, they should be doing the job of fertilizing the plants all on their own. And if we come in and really disrupt that soil environment, then we might have a soil that's much more depleted of its nutrients, and then we might find ourselves looking around to see what kind of fertilizers we can add. So anyway, that would be a role of microbes. Okay, this is getting kind of long. I only have a couple more though. I'll be done soon. Okay, so another category in our CLORPT soil forming factor equation, R is relief, which I said is also a word for like topography or slope. So this tells us kind of like the shape and the slope of the landscape. And in general, you can imagine that soil doesn't build on a steep slope as well as it builds on a kind of a flat environment. And even if that flat environment is up high in a mountaintop where it's probably exposed to more like wind and gravity, that flat environment also may not accumulate as much soil as like a valley bottom. And so basically your landscape position is going to affect your soil as well. And so in general, these soils that form on steep slopes are going to be much shallower and less developed. So in this case, we have an A, B, and a C horizon, but they're relatively shallow. And then here we have an A, B, and C horizon that are much more deep than on the steep slope, kind of on this upper slope position. And then on this valley bottom position, we have an A1, A2, BT, BTG, CG, C. So we have a much, a deep and then also really well kind of developed soil profile in these kind of valley bottom positions. So again, if you're farming, you're probably going to want to be farming here, not here, and here even more than here. So that is something that's probably fairly intuitive as well. All right, last term, well, P, we're skipping over because that's parent material, and we've already talked a lot about the influence of parent material. So we're skipping over that, and we're going to go to time. So time is, of course, just the background by which all this stuff is being measured. And I think it's not a surprise to anybody that the more time you have, the more soil you're going to develop. So this particular diagram from the text is kind of showing rock that is originally, or parent material that's originally being weathered to form soil. And so this is showing like maybe after 100 years of that rock being exposed, you might have some lichens and some small little pockets of grass developing there. And then maybe over like thousands to tens of thousands of years, you're going to start to develop soil. And then that is a process that could be going on for hundreds of thousands or millions of years in the same place if you don't really have a super major disturbance like a glacier coming through or a volcanic eruption or sea level rise or something like that. So soils are resources that take long times to build. A kind of another common soil fact is that it takes, in an area that already has soil, so in an area that already has some soil and vegetation, which we know helps build soil faster. It's easier to build soil when you already have soil than when you don't have any soil, basically. But in those kinds of forested soil environments, it takes about 1,000 years for the natural environment to add 1 inch of soil. So that's a long-term investment. And then if we come along and make some sort of land management decision that's going to lead to the erosion of a foot of soil in one major storm or in 1 decade, we're losing 1 inch is, or 1 foot is 12 inches, 12,000 years of potential soil development. So it's really not a renewable resource kind of in the scale of human life and human society. So that's not to say in very concentrated specific areas we can't do things to build soil, you know, on our farms and in our gardens, but on a landscape scale, that's really a process that is kind of a much slower occurring process. Okay, so climate, organisms, relief, parent material, and time are these 5 soil forming or state factors, soil forming factors that are incredibly important to influencing the development of soil. All right, that's a good stopping point.